Okay, students, it's a 8:45 on a Wednesday morning. It's a beautiful sunny day out there, and I'm sitting again here alone at my desk. I see people are dropping in the live stream. That's good. So we continue our lectures, and you already see the topic, but first let's do some administrative thing, because we changed from our usual schedule on what was it, on a lecturing on a Tuesday to lecturing on a Wednesday, and that was just due to all these roster problems. Hopefully it's not a problem for you early in the morning. For me it isn't. The schedule for the homework, and that is important, is of course adapted to that, in the sense that the handout is again here on the Wednesday. The hand-in is the next Wednesday, of course, and then, and this is important, when have the reviews have to be done, and when is the reflection open, that's on a Sunday night, you could say, from Sunday to Monday. So that gives you that whole time slot on Thursday, Friday, Saturday, Sunday to do the reviews. And then you have until Tuesday night, Tuesday to Wednesday, to do the reflection. So we shifted the whole thing a little bit. I think give a little bit more room in the review. Well, anyway, please check out this schedule very closely. Then let's go to the lectures. Yeah, so we had the spring break, right? And we're now on Wednesdays. One day will drop out, this Liberation Day thing. And then the last lecture I probably won't need, and that could be exam prep. And I really hope that we can do just a regular exam in the computer room at the university, because all other ways of doing examination and proctoring is actually horrible or difficult. Okay, now that's so much for administrative thing. Let's kick off and go to the topic, the subject of today. Okay, let me get my iPad. As I wrote here, Lecture 7, so April 21, Closed Loop Systems and Coordinate Projection Method. It's chapter 15 in the book. And of course, again, with only one hour lecture, I will not be able to cover everything, but it's very closely laid out in the book, so read all about that. Okay, why are we going to talk about closed loop systems? Well, finding, if we go back in this TMT method, then finding this coordinate mapping, finding this mapping which says, well, I have the COM coordinates xi, and I find this nonlinear mapping to my generalized coordinates, is for closed loop systems actually not so easy. Not so easy, and that is really an understatement. And let me show an example. So let's take this for example, this, for instance, this 4-bar mechanism. 4-bar mechanism. So how does a 4-bar mechanism look like? Well, we have 4 bars, of course. This is one. Then we have a second one, like this one, third, and then of course this is number 4, right? The solid ground. So 1, 2, 3. Yeah, you could say this is 4, but it's just the ground. Okay, bodies have center of mass, right, and properties. Now, how many degrees, so if we would use a TMT method, we have to find out how many degrees of freedom do we have to get our set of independent generalized coordinates. So the number of degrees of freedom in this case, well, you can use your mechanical intuition, and that works for most people. However, we also have math. So if we combine the two, we have sort of like a Kalman filter approach. We have a model and we have our intuition, and then maybe we can even come to a better solution. Okay, So first let's do the model we have, and the model is we just count the number of bodies, and we count the number of and then we subtract the number of constraints, and it gives us the degrees of freedom. So for every body I have 3 degrees of freedom, and I have 3 bodies. I have 1, 2, 3, 4 joints, and every joint has 2 constraints, right? It's in the horizontal and in the vertical direction. So minus 4 times 2, and that is 1. So there should be 1 degree of freedom. Now the other thing is my mechanical intuition is, oh yeah, if I turn this crank, then this thing will move, and this thing will, but this is also a crank, that you could say, oh, these are 2 cranks, and there's a constant distance between them, so there's only one way for that to move, right? In your mind, you let the thing move. Okay, so 1 degree of freedom, I sort of agree on that. So then our generalized coordinates, in this case we have to choose a number. So let's say for simplicity we take this angle alpha. Now our job is of course to write down now our coordinates of the center of mass as a function of this one alpha, right? So what are the coordinates of the center of mass? These are just of all these 3 bodies, meaning we have x1, y1, phi1, x2, y2, phi2, and x3, y3, and phi3. And our generalized coordinate qj is just this alpha. To really do the problem, we of course have to need some dimensions. So you could say, well, the length of this guy is a, length of this guy is b, and the length of this guy is c, and then the support distance is d. So then we have enough kinematic data at least to calculate our problem. Okay, so what we have to do is we have to find qi is ti of qj. And well, that's actually not so hard, right? Let's start with body 1. So x1 is we have this length a, and it's let's suppose it's in the middle, the center of mass. Then that's a over 2 times oh, we don't have a coordinate system yet. Oh, I hope Heike is not watching. Don't get mad at me. Yeah, so this is better. And maybe we put also like an inertia frame later on for dynamics. So again, the a over 2 times cosine of alpha. y1 is then of course a over 2 sine alpha. And then phi1 is yeah, this angle alpha. Okay, that's not so hard. Then, yeah, the next one, x2. Well, we travel first to this, and then we take this part. So that's a times cosine alpha plus, yeah, well, plus b over 2. I know that too. And then, yeah, I need this angle, but this angle is of course a function of this angle. So I have to do some geometry, right? Meaning, okay, I can do that. So I draw this line A at an angle alpha, and then the other line B, and then the other line C. And this was the distance D, right? And now what I need to know is I need to know this angle. Well, let's call it beta. But we know it's a function of alpha. So we have to do some, and likewise of course for the next body, right, for this one. You could also say, oh yeah, this is minus comma, and this is also a function of alpha for the input angle. So now we have to do some geometry, and the only thing we have is this distance and these length of the bars. So if I remember well from geometry, you have to build all these triangles, and then with sine and cosine you have to start. So well, let's complete this triangle, and then we draw this line, and now we have 2 triangles. And usually you also want to make like a triangle with a straight angle, because then you really can use sine and cosine. And yeah, actually this is horribly difficult, to say the least. Well, I can calculate what the length is of this guy, because I know this short distance, I know the total distance d, so I know this in between, I know this height, and that's all a function of alpha, so I can calculate what the length is of this as a function of alpha. And then probably if I know what the length is as a function of alpha from this one, I can use like the cosine rule or the sine rule to find out what these angles are, because I have a triangle with three sides and the length of three sides, and then I know that cosine alpha divided by a is equals to cosine beta divided by b, and etc. But I don't know it by head, and it's a tricky problem. So let's look in the literature, right? Okay, and I know that in this case there has been work done, and this is then the work done. Yeah, it's the analysis of a single 4-bar linkage. Okay. So analysis of a 4-bar linkage, and it's by Guy J. Talbourdet, and he's from the research division of the United Shoe Machinery Corporation. Now, what do shoes have to do with 4-bar linkages? Well, to manufacture shoes you need machines, and in the old days machines were just with sticks and hinges, just doing things, right? Like this, and with cranks and sliders, and also for making shoes. And so they needed to design these mechanisms, and you could say that the grandfather of all mechanisms is like the 4-bar linkage. Yeah? With a 4-bar linkage you can almost get any motion. Well, not exactly any motion, but a lot of different motions. And why is that so nice? Because, well, you have a rotating input, and then you have some oscillating or rotating or reciprocating output. Yeah? So if this is the input, then this is the output angle, or a point on the driving crank, or a point on the connecting bar. And then you can generate everything. And actually, there's a wonderful book on this, and it has, usually I take it to lectures, this thick and this big, and it's what we call an atlas of maps of 4-bar mechanisms. Yeah, and I'm going to show you, because I really like this. We can take the time. No, we're going to talk about lecture 7. Yeah, this is the one. Yeah, so this is the book. Let me make it a little bit. Oh, come on, guys. Yeah. It's called Analysis of 4-Bar Linkages. And if you look here at the PDF thing, oh, I want to see myself. Yeah. It's 743 pages. So bear with me. It's 743 pages on a 4-bar linkage, right? So now, what is in the book? Here. What is in the book? It's by Mr. Rohn and Nelson. From when is it? The date? Yeah, it's MIT. The date is on the next page, I guess. Well, anyway, it's 50 something. So here you see a 4-bar linkage, and what did they do? They analyzed these 4-bar linkages and made plots of all points on this connecting bar. Points which, when you turn the crank, which the path you can generate. By the way, here you see a thing which we're going to come back to in a second. And these are the pages. So you have like a mechanism, you have dimensions, and then you have a certain path, and the book is actually very smart because it has a dotted line, and the dotted line gives you information on speed and acceleration, because at equidistant points from the input crank, they write a small stroke, and then keep an opening again. Anyway, I don't have the time to discuss it, but it's actually super cool. This was the way before the use of computers that we were designing mechanisms to get certain motions. Okay, let's get back to that topic of the 4-bar mechanism, the analysis. So how do we find the output angle, or this angle, as a function of this guy? Well, again, as I said, you have to go into this math of sine and cosine, and this k is actually this distance, and then you see all these formulas, and to be honest, it is rather complex what you see in the end. That the one angle as a function from the other angle, it's a phi is an arc tangent plus an arc cosine of things with square roots in it, so they can go horribly wrong too, square root out of a negative number. Then you get imaginary mechanisms or imaginary motion. Of course, it has to do with that the thing doesn't fit, but that the bar lengths do not fit. Anyway, you can continue. You can, from this expression, you can find the speeds. This is actually this Jacobian thing, and then convective terms you can find. And you see it explodes, right? And it's tricky because it will take me, also me, some time to really derive this correctly, right? Okay. Why am I showing this? Well, the bottom line of the thing is, even for this simple 4-bar mechanism, it's too complex. Remember that even if you have more sticks and hinges, then it's just undoable. Okay, so what is the solution for this problem? That is the big question. Solution. Well, remember our most powerful instrument? The scissors, right? This is the solution to all your problems. Watch it. So what are we going to do? So we're going to take oh yeah, I have to. So this is the solution. And, or we could say we do the Napoleon approach. Napoleon approach. And that is divide and conquer. So how are we going to divide and conquer? Well, if this is the, let's make a sketch again of the mechanism. We have this one bar, we have the other bar. We have this final bar, and then we're going to make a cut, and you can cut it anywhere. You can cut it open or whatever you like, but you can cut it here or here. But I mean, a sensible way to cut it is at the joint, of course, just like you debone a chicken. You get it apart, because and then the joints are easily flying apart. So hopla, you cut it here, and when we do that, then we end up with the following system. So we have then a bar with one thing, and then the other one, oh, oops, the next one, and then the next one. We have an open loop system, and on purpose I draw this here, and I draw this here. And now with this open loop system, we can do that. That is super easy. Because for the open loop system we just introduce coordinates. We have alpha here, and let's say we have comma here. No, that is beta, of course. And then here we have minus comma as an angle. Body 1, body 2, body 3. Of course, we have an opening here, right? We have two things which we cut, which we have to fix later, but we can do that. Remember what we have, our magic potion. So we had our glue here. Glue is the, apply the glue here. So this was the glue. So we're going to put that glue later on here to fix it again, to get back to our system. So now what we got is A, B, and C are the distances, and this is D. We now got 3 degrees of freedom as an open loop system. And for that system, it's super easy to write down your equation of motion, your kinematic equations. So 3 degrees of freedom. Your Qj being now alpha, beta and gamma, plus 2 constraints. And the 2 constraints are, let's call this point D, that the delta x of D should be 0 and the delta y at D should be 0. And then if we glue this all together, then again we have our original system. And these 2 constraints take away 2 degrees of freedom and we still have a 1 degree of freedom system. But we do that because now writing down xi is Ti of Qj is super simple. If we proceed again like in what we had here, x1 was a over 2 cosine alpha, y1 was a over 2 sine alpha, and phi 1 was alpha. And then x2 is, of course, we start from that point, a cosine alpha plus b over 2 cosine gamma, y2 a sine alpha plus b over 2 sine gamma, and phi 2 is beta, the absolute angle, and x3 is, a cosine alpha plus b cosine beta plus c over 2 cosine gamma. Well, let's finish it up. A sine alpha plus b sine beta plus c over 2 sine gamma. That's good. And then of course phi 3 is this gamma. And then of course plus the glue in our case, which are these 2 constraints. And the constraints are, as I said, delta x at D should be 0. Or in other words, then we have to calculate what is the position of this point in the x direction. And then, well, we can borrow this expression, of course. Then we say a cosine alpha plus b cosine beta plus c cosine gamma. I use a shorthand notation, by the way. Minus this distance d, right, is 0. That's one constraint. And the other one, in the y direction, we get a sine alpha plus b sine beta plus c sine gamma minus 0, because 0. So, and then this together with this gives our original system. Or in this sense, these equations are C, what did I say, CK QJ is 0. So with this one and this one, we now can build up our system. So now we can build again our constraint, our differential algebraic equation of motion. And how do they look like? Well, they look like any constraint equation system, right? Where we have like a mass matrix, but this time of course a one which is transformed. I will get in a second. We have this Jacobian here from the constraints. We have a lot of zeros here. Then here we have, we do not have q x double dot, we have q double dot, right? Because we have this set of generalized coordinates, and they're not independent. If I had independent generalized coordinates, I would have 1. We have a set of generalized coordinates, in this case 3. Q double dot. Then we have Lagrange multipliers. In this case, since we have 2 constraints, 2 being the forces horizontal and vertical at that joint. And then on the right hand side, we of course have our Q bar from the TMT method, and then minus our C, Q dot, Q dot, our convective terms. And let's supplement that with being clear what is M bar. Well, M bar is then of course this transformed T, well, maybe I'll write it like this, T, Q, what is it, transpose times M times T, Q. This is our transformed mass matrix, where this is just the mass matrix on the basis of the center of mass coordinates, and our Q bar is likewise also with this, you could say with the forces which are dual to these degrees of freedom, 3 in this case, at torque m alpha, m beta, m gamma, and then minus T, Q transpose times the forces, I write a capital, not an I, sorry, the forces applied at the center of mass, minus all these convective terms, right? G, I just call them G. Yeah, convective accelerations. And that compromises actually the way how you can solve that. And now with a small set of generalized coordinates, they're not independent, but with a small set you can solve the whole problem. So what is the scheme? So from the DAE you solve for Q double dot and these lambdas, right? You get those lambdas for free. And then you do a next time increment. So, and how do we usually write that? Because we do numerical integration, because we are interested in the motion. So we say, well, I do my Qn plus 1 is my Qn plus my Q dot n times, what did I say, delta t or something like that, delta. And then my new speeds are of course my old speeds plus my accelerations times delta t. And therefore you need this equation of motion for this guy, because this is already a state variable, but this is what you get from the equation of motion. And then you've updated, then you can close the loop, you can go back again, formulate the equation of motion, calculate the whole shebang, and do a next step, and then ad infinitum. And you will have the motion. Okay. But something is rotten in the state of Denmark. Rotten in the state of Denmark. And I have nothing against Denmark. But what is going on? Well, if we now look at these coordinates and these speeds, you will see they will not fulfill the constraints. So this if we calculate the constraint Ck of this Qn, then you will see they will not be 0. Small, probably, but not 0. And likewise, if we do that with the velocities, then they're also. So you could also say that this Qn is this Qn plus 1 is an estimate, right? This was a good one, but this tilde means it's an estimate. So we know approximately what this thing is. So it's an estimate, in the sense that if we now calculate what these values are, they're usually not 0, and they should be 0. Now, and likewise, of course, for the velocities, right? This is our double. Our state is position and velocity. Q double. And did we make an error in the calculation? No. We set up our equation of motion correct. We did with enough accuracy, etc. But the thing is that this numerical integration is an approximation, and nothing guarantees us that these coordinates or these speeds are fulfilling the constraints. And there's actually a nice picture which goes by that. You could say that the new estimated position and speed from the numerical integration does usually not fulfill the constraints. Both on the constraints, of course, on the position and on the velocity level, but that's clear. And there's actually we've seen that, and let me repeat that, how we've seen that. So here, where am I? Yeah, here, lecture 7. Where is the movie? Okay. Here's the movie. Oh. Come on. Play back. Ah. Repeat. Yeah. And now we do it again. Okay, here's the movie. Remember? Here, where we have this motion. Let me see if it's visible. Yeah. Then we see, of course, that a gap occurs here. And of course, if you make the numerical integration step smaller, the gap will be smaller, but the gap will come, whatever you do. And if you continue in numerical integration, the gap will become larger and larger. So we have to get rid of that. So after every numerical integration step, we have to correct something. So you can also draw that in a nice way by saying, well, the constraints are like a surface. So this is what we call the constraint surface. And think of Earth. Earth is our constraint surface. We have to move over Earth. We are in three-dimensional space, but we are bound to, well, not unless you can fly, but we are bound to move on Earth, on this plane. Then we had initially a very good position here. Let's call it Q0 for now. And then by numerical integration, you found some point here, which is Q1, and I put a tilde there. And then when you calculate, you see that it's not on the surface. So we have to get back to the surface, but there are 1,000 ways to get back to the surface. So if we calculate C of this estimate, it's usually not 0. But there are like an infinite ways to get back to the constraint surface. And how are we going to do that? Well, and this surface, you can also write this is CK of QJ. How are we going to do that? Well, the most intuitive way would be, of course, let's take the shortest distance. So shortest distance is this. So this is then probably our best guess for Q1. The shortest distance, the shortest distance between this guy and this guy. So we want to say that, well, if we formulate it, this is the true position, and minus the estimate position, this should be minimal, this distance. And that is the best way to do it. Now, how do we do that? Well, that sounds actually like an optimization problem. So let's formulate that optimization problem. Oh, don't do that. I don't want to focus. Yeah. So it's actually an optimization problem. So we have this estimate, Q tilde 1, and we want, of course, C of Q1, and I dropped the vector thing, and now for now make it a little bit simpler. And now what we want to do, we say, well, the real one, which we don't know, of course, minus the estimated one, the norm of that should be minimal with respect to what is our variable, that's Q1, but it's subjected to the constraint, because we want to get on the surface, we cannot go anywhere. Otherwise, the best solution will be the Q tilde itself, then the distance is 0, but it's subjected to C Q1 is 0. And this is what we call a constraint minimization problem. And such a constraint minimization problem, I'm not going to derive how you do that, but you can solve that. It's a non-linear, linear constraint optimization. And that's a difficult problem. So the first thing, why non-linear? Because this is a non-linear one. And why constraint? Because we have constraints to this. We can get rid of the non-linear by going to approximate a linear problem. So we linearize the whole thing. So our constraint, we're now going to linearize our constraint. So we're going to say, well, this Q, this Q1, this is a good one, the approximate precision plus some delta. And then the problem is to find this delta. Or in other words, if you look at our modernization problem, we say, oh, the sum of the squares of these deltas should be minimal with respect to Q1. And then what is the constraint equation? Well, we then linearize this guy, and the linearization of that guy is, of course, that C Q tilde, which is not 0, plus the Jacobian CQ time at Q0, oops, at this approximation. Well, let's drop that for now. It's far too complex. So that's the Jacobian of the thing, the tangent thing, times delta Q. Delta Q1 is 0. So that is our constraint, a nice linear constraint, or you could also rewrite it as a matrix. This Jacobian times the delta Q's is this minus C of this approximate one. So this is a linear constraint to this problem, and you can solve that problem easily. And yeah, the solution, you could say, of this Gauss-Newton process. Well, why Gauss? Because it's optimization, it's a minimization problem, and Newton because we linearize. And you can read, for instance, Langsos on that to see how that actually goes. But I'll give you the solution to that, and it's what equation do we get? Well, we get the following one: I C comma transpose C comma Q zeros. Then we have delta Q's here. We have mu here. And on the right hand side we have zeros and we have minus C, this Q tilde. So that is the solution to our problem. This minimizes this distance under this constraint. And of course, since it's nonlinear, we have to do this probably a few times, but it's a Newtonian scheme, so it has quadratic convergence. So that should go very quickly. Now, a very smart student in the audience would probably say, like, hey, I remember that equation, because this was like a mass matrix, this was Jacobian of constraints, and these were Lagrangian multipliers, and then the answer is, yes, you're absolutely right. Mechanics is also like a Gauss-Newton type of solution to an optimization problem. And what is the optimization problem? Well, isn't it that you want to have the shortest distance? Is mechanics not always that parts fly the shortest distance? They go from A to B when they have a certain velocity. They don't take all kind of side routes. You can formulate mechanics as an optimization problem. So you can go up to a certain level of energy and say, well, the energy has to be minimal, and that is the solution for which the motion will move. That's not the topic of my lecture. That's even of these lectures. I'm not going to talk about that, but you could also look at mechanics in that way. Back to this. So, okay, we now formulated the problem, but we're of course more interested in the solution, right? So for the solution, I'm going to do for now a shorthand notation to show that the solution is actually not so tricky. So I C transpose C zeros. I'm going to call these just deltas, and this mu, I keep that. And then here 0, and then minus E, like error, because the error we have is this C of this Q tilde. Okay, so this is the shorthand notation, and I want to have the solution. Well, the solution is actually super simple. In this case, you can just take the first equation, and the first equation reads I times delta plus mu C transpose is 0. Or in other words, I know what delta is. Delta is minus mu C transpose. And then what do I do? Then I stick this into the second equation, and go back. And the second equation reads C times delta equals minus E, right? So then put that in, so C, and tell what on the minus times C transpose times this mu, that was a vector of course, right? Equals C times delta, this minus E, right? And I can solve that then. I can say, so I have a matrix, C transpose mu equals Fe, and then the solution to that is of course mu is this C times C transpose to the power minus 1 times E. And then the big question is, can we do that? Can we do this inverse? So can we do that inverse? Well, the number of constraints, this is always a matrix which has a few rows and more columns. Because it's about more variables, we have less equations than we have unknowns. So if you then calculate this, so for our 4-bar mechanisms, the C at the space we had 2 constraints, so it was 2 constraints and we had 3 degrees of freedom, right? 2 times 3. So this in the end is a 2 by 2 matrix. So yeah, that should work. If it has full rank, it should sort of work. So we can invert that guy, we can find what mu is. We want to know what delta is, and then of course the increment delta is minus mu times C transpose, so minus C transpose times C transpose to the power minus 1 E. And this is the solution for our Gauss-Newton process. Now there is actually a name for this. We call this guy, I have a name for that, yeah. This matrix, this C transpose times C transpose to the power minus 1, we call that C plus, or we call that the Moore, and it's not from Jason Moore, but from another Moore, look it up, Penrose inverse. So that's the Moore-Penrose inverse. And the Moore-Penrose inverse, it's defined like this guy. And sometimes in MATLAB, if you do backslash, then you get this guy. But not always. It depends a little bit on how the problem is defined. Okay, well, this looks like magic, right? So let's kill the magic and make it more clear. And I'm going to do this by example. But before I do that, let's talk about the scheme. So the scheme is as follows. We have to go back. What were we doing? We were doing the following thing. We wanted to solve a 4-bar linkage. We couldn't do that, so we had to cut it open. And we have 2 openings. So now we can formulate the equations of motion pretty easily for this open loop, but we have to add the constraints. We formulate them, that's easy peasy. I do a numerical integration, but then I'm stuck with the problem that I get a drift of my solution. It slowly will move away from my constraints, and I don't want that. I want to have accurate results. So then I can project them back on the surface. And how do I do that? Well, there's a very simple mathematical trick for that, and that's called a Gauss-Newton approach. By doing the Gauss-Newton approach, you make sure that you have the shortest distance to the constraint surface, and then you finally find a solution on the constraint surface here which fulfills the constraint and which has the smallest difference with the estimated one. And you would say, oh, but first we make a numerical integration solution and then we tinker with that solution, so is it still accurate? it has been proven that the error you make in this, we call this coordinate projection method, by the way, in the coordinate projection, the error you made is of an order higher than the error you already have in the numerical integration. So it doesn't matter, that error is already in your numerical integration scheme. Well, at least if you don't take two big steps, but when h, delta t is small. Okay, now how, there is an example in the book which clearly shows how this works. And the example is sort of fun. And I will start with the example. But I probably will not have time to finish it. Well, yeah, I need some 10 more minutes just to get you hooked up on the example. And the example is the following. I have two constraints on 3 variables. And for now I do very simple linear constraints because, yeah, just to show this one step. But it's and what are the two constraints? Well, the first equation is x1 minus x2 is 0, and the second equation is x2 minus x3 is 0. Okay? So I have 3 variables, x1, x2 and x3, and these are the equations. I have an estimate solution, so estimate solution, oh, it's a vector, x1, x2, x3, yeah, with a tilde, and the estimate solution is 0.9, 1 and 1. Now you immediately see that these equations tell us that x1 should be equal to x2 and x2 should be equal to x3. So of course we know the solution, super simple, but that's how we can understand what's going on. And then we see here we have an estimate where not all the numbers are identical. Well, you can even, if you form nicely what is the ck of xi, and these two equations, x1 minus x2 and the other one is x2 minus x3. If I then determine what are the constraints of this estimate, what are the values, then the first one is x1 minus, so that's minus 0.1, and the second one is x2, that's 0. But it's not all 0, so we have to solve that. And of course a smart mouse would say make them all equal. So a solution, and I say a, I do not say the solution, but a solution would be that the real x is 1, 1, 1. But then the question is that the nearest one to this solution? Is that the shortest one? Now you can make drawings, of course, in a 3-dimensional space, and then draw this constraint surface, and then with geometry do that. But we don't need geometry. We can formulate our problem, right? So the answer is, if we go from x is this x tilde plus delta x, and in our case, in this case, the delta x is what is it, 0.100, and is that the smallest one to get us back, or is there even a simpler way to get back? And my gut feeling says there must be, because now we only tinkered on this one, but if we tinker on all the elements we can probably make this one smaller. Anyway, we know what the solution is to our problem, right? So if we then formally write our increment delta x1, delta x2, delta x3, we have to take the Jacobian of these equations, so that's 1 minus 1, 0, 0, 1 minus 1 equals, and in this case, yeah, we have to put the error there, right? So what was the error? Oh no, we're solving, of course, the increment problem. So on the right hand side we have to write what is the error in the constraint, and the first error in the constraint is what is the error in the constraint? So we have to do a minus 0.1 and a 0 here. Or a plus, because we put the arrow on the other side. Okay. So how we're going to solve this C delta x is E, right? Again, with this more Penrose inverse. So we get delta x equals this minus C transpose C transpose to the power minus 1 E. And we can form this matrix, right? So we have to form the C transpose. So this times this guy. Well, that's super simple. If you do that, that's 2, 1, 1, 2. And it's symmetric. Yo, I'm happy for that, because if you do the transpose of this, you should get the same. By the way, it has a minus here, because this times this is 2, and then this times this is minus 1, this times this is 2, this time this is also minus 1. Yeah, so 2 minus 1 minus 1, 2. Then we need the inverse of that guy, so C transpose is to the power minus 1. This is the answer, 2, 1, 1, 2. I agree, because you need the determinant is 2 times 2 is 4, minus 1 is 3, 1 over 3, and then the diagonal terms, and then a minus for the odd terms. So that looks good, and of course you can check it by multiplying with this guy. So we formed that guy. Then we can say, oh yeah, now the delta x is this minus C transpose is this, what is this, 1, 0, minus 1, 1, 1, 0, 1, times this 1 over 3, 2, 1, 1, 2, and then times the error, which was 0.10. Well, a lot of calculations, but in the end, the answer will be delta x equals 0.1 times 2 over 3, 1 over 3, 1 over 3, and this has a minus sign. And lo and behold, if we now calculate the new position, that is going to be our 0.911 plus the 0.1 times 2/3 minus 1/3 minus 1/3, and that equals, so that new position now equals 0.9, and then there's a lot of 6's, and this is 0.9 with a lot of 6, of course, because they should be all the same, right? Anyway, we see actually what happens, that we add a little bit to this and subtract a little bit, add a little bit to this and subtract a little bit to this. And now the question, is this really the shortest distance? So what is the distance between the tilde minus the tilde? What is that? If we calculate that, then our answer will be, so we have to calculate this one. Well, the norm of 2/3, 1/3, and 1/3 is a square root 6 over 9, so that's less than 1, right? So yes, this is a shorter distance than just adding 0.1 to this guy. So we call this coordinate projection method. And look it up in the book. You have to do that, of course, not only on the coordinates, but also on the speeds, but for the speeds it's actually super simple. Okay, yeah, 1 minute left. So that compromises the topic I wanted to talk about today. Read chapter 15. And then, so I say, I should say, read chapter 15. I'm going to write it out. I'm going to use chocolate letters. Read chapter 15. Read chapter 15 and you see all the details. And then do homework assignment 7, and within next week. We do a couple of minutes break, 5-minute break, and at a quarter to 10, quarter to 10. I'm still not used to the new time schedule. At a quarter to 10 we continue with the questions and answers in Zoom. Thank you for your attention. Okay, where's my mouse?